I'm glad to be here, actually. So this is pretty nice. Can you tone this down slightly? So the great thing is that I have two topics, essentially, as Pete already summarized. Network interconnects on-chip and off-chip. But I'll stay pretty abstract. So I'm not going to tell you much about the numbers, the speeds and feeds, because you've just heard about it. So what I will tell you is what actually matters for algorithm design, so what matters for thinking. So I'm going to tell you a little bit about a more abstract model of how these things work, of how you design algorithms in these things. So we're going to ignore a lot of details, but you should ask about the details. So you can interrupt me at any time. So what I actually want to do in the first 2 minutes of the talk is to evangelize you a little bit. And you've heard all these hardware details and all these things that you're like, so many megabytes per second. But what I really believe what we should be doing is we should be optimizing our performance in abstract models that we can understand. So for this, the key is actually mathematics. So mathematics here is really in the sense that we design a mathematical model of how our system looks like. Because only a mathematical model, remember mathematics is really the key to abstraction and makes things easy and easy to grasp. Right? So if I tell you about a microarchitecture, you will have a rather hard time writing an optimal code for this microarchitecture. And it'll actually be close to impossible for you to prove it to me that your code is actually doing well or optimal on this microarchitecture. Right? So what we can do then is we can define a problem on this architecture. So for example, we want to solve our whatever PDE on this architecture. Right? It's pretty easy. We can now, in this mathematical model, we can find a solution. And this is a mathematically sound solution that we can now find because we have a mathematically sound model. I will give you an example later. This is still extremely abstract, I know. And then you can implement this mathematically sound solution in your code and then run it and see. And then you realize, well, my system model was junk to begin with. And then you can refine and do the whole process iteratively again, unless you feel you're close to the expected performance. And there are many ways to do this. So one popular example is the roofline model. So I assume this is covered somewhere else, but I'm not talking about the roofline model, of course. But this goes along this circle, really. You're trying to get too close as possible to the roofline. Here, I'm going to talk about networks. Right? So, and I'll talk about a little bit about techniques and how to actually do this in practice. So, but what you learned in school, I assume, is much about computational complexity. So you looked at how can I actually make algorithms as fast as possible. So if I do a matrix multiplication, I may not want to do the n to the cube matrix multiplication. But if you're crazy, you may do a Straßen-Vinograd or something like this with a much lower complexity. But well, recently we were told we have to forget about this because everything is now a different kind of complexity. So who knows what the red-blue pebble game is about? Who has heard that term? OK, there are two people who know what it's about who has heard that term before. Oh, wow. So it stays with two people in this room. So this is actually about input-output complexity. This is something that people recently start caring about. And it really means what is the minimal number of data transfers between computational elements that I have to perform in order to solve a computational problem. Right? This is something that gains more and more importance recently because machines grow. We've talked about networks. And of course, these input-output, all this stuff goes through a network. So we want to minimize the load on the network because the network is typically the weakest component in the system. That's just a quick introduction. So people have been designing cache-optimized algorithms since the 70s, so we know about this. Recently, people came up with communication-reducing algorithms. So Jim Demmel and folks who will actually be here later will tell you all about this. So this is kind of a starter for this. I'm not going to talk about this. It's just an overview. And what I'm proposing a little bit here is actually that we want models that combine computational complexity and input-output complexity. And I'm going to give you some examples of how to design algorithms in this model. Okay? And then at the end, you'll get to model-driven algorithm design. But that's something that many people drive. And also, I'm sure Jim will tell you something about it. OK, cool. So let me give you a first example that is actually that has been used since a long time ago. So it was published in 1996. Actually, the model itself was published in 93. And Optimal Solutions were published in 1996. So this is a model for networks. So I told you I'm staying in an abstract level. Right? I'm not going to talk about whatever InfiniBand, Ethernet, the Blue Gene network, or something like this. I can give you all the details if you want, but I only have 45 minutes, so I cannot. So ask me in the break. What I want to advertise, though, is that you can use this computational model, which consists of, well, 1, 2, 3, 4 parameters, maybe 5, to solve most of your algorithmic problems. So it is way too complex to think about what is the bandwidth of my network, what is the latency of my network, what are the exact parameters, what is the topology. And people in 93, which was before my time actually, came up with this very simple model. It's actually a very famous person, Richard Karp, who also proved a lot of things related to P versus NP. And he and another group in Berkeley came up with this model to model networks how they existed at this time, and this model is still very accurate today. So what you can do with this model, and it's extremely simple. So let me, to demonstrate how simple it is, I'm going to do it on the whiteboard. I hope you can do it, and you can see things. So you have a sender and a receiver, and this is time, okay? So the sender invests O in order to issue a message. The message goes into the network, and this is a simplified version of the log-P model. The message goes into a network, travels at latency L, and then arrives at the receiver, which again has to pay O for the message reception. Okay? Here there's another G somewhere. Let's just ignore this for now. In the original model, there's a G. I'm making the assumption for the experts that G is bigger than O. So who's familiar with the log-P model? 2 people. And lecturers, yes. So, OK, good. Then you're learning something new, right? So this is a timeline. OK. So let's now solve a simple problem in this log-P model. So again, the model is like this. If I'm sending a message, I have to pay time O. I'm paying time L for the message to travel through the network. And I'm paying, again, time O to receive the message at the other side. OK? It's a very, very simple model. And now let the problem be broadcast. So broadcast means there's a single process that has a message and wants to send it to all other processes in the network, right? We have P processes. That's the P. By the way, in the log-P model, P is always kind of useless because it's really just a number of processes, but you need it as a variable. It's not a system parameter, OK? Who has a good idea? How would I do this? How can I distribute a message from a single process to P minus 1 other processes? In a tree. Perfect. What tree? Binary tree. I see. So you say binary. So you can remember this, I hope, right? OK, let's see. Binary tree. So binary tree looks like this. Right? So we all know binary tree, I hope. Good. Do you think this is optimal? OK, what is optimal? Why are you telling me binary tree if you know that it's not optimal? I mean, come on. OK. It's a good starting point, actually. It's asymptotically optimal. But I want a strict optimal solution. So who can give me a strict optimal solution in the model I just discussed? Because a binary tree will essentially be like this. 0 time here, L plus 2O here, right? And then L plus 3O here, L plus 4O here, L plus 5O here, and so on, right? That's a binary tree. OK, so what is a better solution?
Is it the picture on your slide?
Exactly.
It is, of course, the picture on my slide. Yes, very good. You're very smart people. OK, good. The optimal solution is very simple, and I'm kind of hiding it there. So what we do is we construct an infinitely sized optimal broadcast tree. So that's an abstract concept, but it's very simple. So it has time 0 here, and it reaches the first process after L plus 2O, correct? I can send the next message after I'm waiting O. So it reaches the second process after L plus 3O, then the third process after L plus 4O, and then L plus 5O, and so on, right? But the fun part here is, depending on the size of L and O, the tree shape will change. Because this guy can send after L, or can send a message after this one arrived immediately, right? And it will get here, L plus 4O. And then I have L plus 5O, L plus 6O. And here I go L plus 5O because it's after the L plus 3O arrived, and so on, and so on. Oh, apologies. Of course, it's 2L. Yes. Thank you. So you're paying attention. Very good. So what is now the optimal broadcast tree? Well, this is an infinite tree that I just constructed, right? So the optimal broadcast tree is actually, if I want to process, I still want to broadcast to P processes, right? The optimal broadcast tree is the P nodes in this tree with the lowest label, correct? OK, if you do this at home, and now we don't have enough time, so I teach this usually in a class, and I teach this at least 15 minutes, but I only have 5 here. So the optimal broadcast tree is a generalized Fibonacci tree. So who knows the Fibonacci sequence? Oh, very good. That's more than 80%. Excellent, excellent, cool. So who can imagine how a Fibonacci tree looks like? Who can explain me what that means? Oh. Yes?
A tree with a number of nodes at each level
follows the Fibonacci sequence. Exactly. And if you paid attention, I said it's a generalized Fibonacci tree. Because a Fibonacci tree is only one specific Fibonacci tree. Here, you need to consider the L's and the O's in order to build the specific Fibonacci tree that you actually care about. So this was a very small example, but it's the most impressive example I know that shows you how powerful it is to use these algorithms. Like, we started with the clearly suboptimal tree. And actually, if I would give the full lecture, I would show you that this is significantly slower than this. Right? Asymptotically, it's the same. But there's a huge constant between these guys. So in like 2 minutes, I demonstrated to you that using this model-guided design is very, very cool. OK, at least for me. OK, good. So now let's, and now you understood everything. Right? You know these L's and O's, and it's all pretty boring. So you can do this yourself. You can do this at home. You can read all the papers. It's well documented. And now I want you to just accept this and move on. OK? So this was everything I'm going to talk about distributed networking, because it's a simple concept. You use this model. You're all intelligent people. You come up with this is the mathematical representation. You come up with an optimal algorithm. There are many interesting design principles. I just don't have the time to talk about this. You know one now. You know these generalized Fibonacci trees now. You can continue this at home or in the exercise session. And now I'm going to show you something that's much more complicated, but much more fun. Oh, more fun, we will see. But OK. So because this applies, I swear, this applies to Ethernet and to InfiniBand and to many of these, at least at an abstract level, many of these networks. Like BlueGene, it'll apply as well. But we have these guys today, right? So, I mean, this is an interlagos CPU. This is a Power 7 or Power 8 CPU. This is a Xeon Phi. This is a Kepler GPU. This is an InfiniBand card. This is a BlueGene network like we've seen a couple of minutes ago. So who can tell me the difference between the top row and the bottom row? They form two groups that have a very distinctive set of features. One feature differentiates them.
Symmetric. The top row seems symmetric.
The top row is symmetric in the sense of SMPs. Well, the bottom row is not really compute, right? The bottom row here is just communication. So you're close, but not quite there. Yes?
They're on and off die?
Oh, they're all dice, but it's close. It's close. You're getting closer. OK, so somebody crack it. Don't have that much time. You heard a lot about these in the morning here. And I just told you everything you need to know about these, at least these. Think about the cache.
Memory access.
Close, close. So these guys have caches, right? And these guys don't necessarily have caches. Another way to say it is that these guys implement cache-coherent architectures, and these guys don't. So can you tell me from a communication perspective what the difference is between a cache-coherent system and a non-cache-coherent system? That's an easy one again. Oh, now I lost you.
It's more traffic for coherent systems.
Yes, but why?
Because you have to keep them coherent.
Because it's, yes, you have to keep them coherent, yes. But OK, you're right. I just express it in different words. Because the communication is implicit, right? You access memory, and then the communication happens in the background. The hardware does not know what you want to do. The hardware has to operate in a very specific model that is well, of course, imposed by the hardware and the constraints that I'm going to talk about in a couple of minutes. But it's really an implicit communication. So it tries to guess what you're doing, and then it does it for you. Right? However, in these models, you explicitly tell the thing, send this message from here to there. Right? It's a huge difference. It's implicit communication versus explicit communication. So explicit communication is that. Right? You know how to do this. You know, use L's and O's and then solve it. And now I'm going to talk about this. This is not such a well-known model, but it's about as cool. OK. So, but now let's repeat a little bit about caching strategies. I know you heard much of this morning. But let me quickly go through this. So you know we have two types of caches, right? We have a write-back cache and a write-through cache. So can anybody tell me the difference between these two guys? It's probably on the slide.
Write-back is to the lowest level of cache, and write-through goes up 4 levels to memory.
Very good. OK, let me just repeat that. The write-back cache, you essentially, when the CPU issues a write, it just goes to the cache and is at some later point in time synced to the memory. A write-through cache, it's immediately written through, right? This is the high-level difference. OK, so and then the funny thing is, I'm now going to demonstrate that you need these two things to consider a system cache coherent. You need write propagation and write serialization. I have two examples for these guys. It's very simple, so just bear with me. So a write-through cache, let's assume in this model we have two CPUs, right? CPU 0, CPU 1, two write-through caches, and one memory. Right? So this is like your standard whatever model, very simple. And so let's assume this X sits in memory and has initially the value 0. Okay, so what do? The CPU reads X from memory. Of course, it reads X equals 0. So CPU 0 has X equals 0 in its cache. Then CPU 1 reads it from memory, also reads X equals 0 because nothing happened to X. Right? Pretty simple. Okay, fine. CPU 0 write X equals 1, and now it gets interesting. So what does CPU 0? It writes X equals 1, so it'll update its cache. Remember, it's a write-through cache, so it'll also update the memory at the same time immediately. Okay, fine. And then CPU 1 now has the idea to read X from its cache. And if there was no cache coherence protocol, CPU 1 would just read 0, right? And it would not actually get the new data. That's very simple, right? Okay, good. Okay. And then what we need for this is we need write propagation. That's the first feature we need for cache coherence. So actually CPU 0 needs to tell CPU, or the cache here needs to tell CPU 1 that the write actually happened and that it reads the new value. I say nothing about timing, by the way. So I know this is probably not so interesting. Write back cache, same thing, right? Just slightly different because what's happening here is, well, we do the same thing, right? We read X equals 0, X equals 0. CPU 0 writes X equals 1, right? Again, X equals 1. And now CPU 1 writes, but it does not write through, right? Because it just writes back to cache. And then CPU 1 writes X equals 2. Okay, so CPU 1 writes X equals 2, and now you have a problem. So now you have two inconsistent copies in these two caches because it's a write back cache, right? And well, and then at some point one of these values will commit to memory, and depending on the order they commit to memory, you will have different values. So now you realize, well, this is a total disaster, right? And to fix this, we need write serialization. Okay, so let's go through the simple example. You learned this morning the cache size, cache lines are 64 bytes. Okay, they have a size. Let's say they're 64 bytes, okay? Let's look at this code. Let's assume this code is aligned, right? We have a struct. It's a C struct, C99. We have int A and int B. And we have two threads, right? So, and let's say at the beginning, A equals 0 and B equals 0, right? And they're on the same cache line, right? Because they're aligned. And so let's now say thread 0 writes A equals 1, and thread 1 writes B equals 1. So assuming the cache models that we had before non-coherent, what would be the possible values for A and B in main memory? Can you tell me? Sorry?
You have 0 and 0, 0 and 1, 1 and 0, 1 and 1.
Can you have 1 and 1? You cannot have 1 and 1. You can have all the other combinations, but not really 1 and 1. Okay, good. Depending on what your cache is. And this would, of course, be a total mess, right? Because we are writing to two different variables, logically. I mean, in my mind, these are two different variables, but they kind of overwrite each other depending on which cache line they're on. So this is just a motivation fee. Of course, this is what you get if you do not have cache coherence. So you may have heard that some people want to get rid of cache coherence, right? So this is something you have to control then. Soon as our friend Intel gets rid of cache coherence, then you have to manually control these guys. There's actually an easy way to do this, so don't get too scared, right? But this is one of the implications of this model. Of course, today, what we have is actually cache coherence. So let me quickly explain how the protocol works, because again, you understand how to program large networks, explicit communication, but implicit communication is much harder to understand. Okay, so the reason why we need cache coherence, to quickly repeat, is that the programmer cannot really deal with this unpredictable behavior today. Or in other terms, let me say this slightly ferociously, Intel wanted to sell multi-core CPUs, and programmers were not fast enough to change their way of thinking to a real distributed mode. So they emulate you a CPU which looks like a single-core CPU with multiple threads, right? Without all these problems. Right? So it depends on the way you see it. And so there are two fundamental mechanisms how you can ensure cache coherence. Right? So it's very, very important. So one is snooping. Right? So snooping is really, it's a simple model that you're running in your laptop, essentially. Well, it's some kind of version. What you're running in your laptop is actually simpler than snooping. So, but you would run it if you buy a multi-socket Haswell system, for example. So what you do there is everything is connected to a shared bus or broadcast network, so every CPU talks to every other CPU, and the cache controller snoops transactions, which means if I'm issuing a write, right, I'm writing to a cache line, I'm telling everybody in my network, in my cache coherence domain that I'm writing to this cache line. And what the other guys do is, well, they check these write signals. They're called bus signals for some reason. And then invalidates the lines that they have locally, right? So that's pretty simple. The other way is slightly more complicated. So this is what we have in anything that we call a CPU these days, I think. So Sandy Bridge, Haswell, and the AMD architectures, all of them use snooping protocols in one form or another. Sometimes they do it in the last level cache. Sometimes they do it across larger networks like QPI, right? But it's conceptually seen, it's all the same. There is a second protocol, which is more complex and thus much more interesting. So it's directory-based. So what you do there is you have a directory, which you can imagine like a distributed hash table, right, in case of your distributed systems background. So directory protocol really works like this, that you have a central place where you put your information of the state of a cache line. So if I want to read a certain cache line, I ask this central place, what's up with this cache line? What's the latest value or something like this? And then you do it. There are multiple different ways you can do this, okay? So these are the two modes. I'm going to talk about the second one. With a slightly more applied way in a couple of minutes. Okay, so how can we now ensure cache coherence? So this is something that you can easily guess by now. Well, the first problem is obviously the problem of stale reads, right? So you don't want to read outdated values. One way to deal with this is, well, you just disallow the state that enables outdated values in the cache. Right? So this is a rather simple thing. So what that means, and that of course you know, you just invalidate all the remote copies. Right? As soon as I write something, I invalidate all the remote copies because I wrote something the other guys cannot know by definition what I wrote. So just kill them all. The second problem is this lost update problem, what I discussed before. Right? So the idea here is really if you have write-back caches, two of these caches can have different values, and then nobody knows how to fix the difference between the two because there is no merging operation, at least not in today's architectures. Okay? So the solution is, again, disallow more than one modified copy. So this is the solution to everything. We only have one modified copy of one thing. So if you look at a little bit more practical implementations, well, what we have today is these invalidation protocols that use cache snoops. Right? So this really exists in today's CPUs, as I mentioned. And another protocol is really the protocol that is based on explicit updates. So the idea here is that I mentioned the central directory. So it doesn't have to be central, by the way. So this is where it gets slightly more complicated, but I'm not going to go into too many details. However, I'm going to talk about a very specific architecture. This is Intel Xeon Phi, which is the first commercial architecture that is available at a broader to a broader audience that uses this. Well, okay, it's the first commercial on-chip architecture. Now I get a little more specific here. That uses this at a larger scale. So you can buy it. You can go out and buy one of these things. And it's a pretty interesting architecture for that reason. And I'm going to deep dive a little bit in that architecture in order to foster the understanding of how these protocols work. And then I'm going to show you the same thing that we can do with this guy. Right? So now you understand how to design algorithms in this model. And I want to make you understand how you design algorithms for a cache coherent system. You will see it is much more complicated in this model. This is why I'm talking about this much longer. Okay? Good. If you have any questions, let me know. Very good. Okay. And it's of course not good if you have no questions, but but let me know. At least you look like you're still entertained. Okay. So now let's quickly discuss another difference. Right? There are also two possible ways that you can enforce cache coherence. Right? I talked about the first way, the invalidation-based. And now you can say, well, I have a cool idea. I come up with a new protocol that's much better than your stupid invalidation protocol. Because if I invalidate your copy, next time you need to read it from main memory, and that's slow. Why don't I send you the new copy that I just updated? Right? I could do that as well. Right? If I write something, I could just broadcast the thing I wrote to everybody in my network, and then it would be consistent as well. Yes, this is actually called update-based. Right? And nobody does that today. The reason is very simple. Because if you write something, you hit a 64-byte cache line. And if you want to broadcast that 64 bytes every single time through your whole bus, and everybody does it at every single write, yeah, you need a pretty big bus for this. And people don't usually have these. So update-based is something that people don't use. You can, of course, now think about hybrid forms and say, well, yeah, you just showed me a bug. I can fix your protocol. Again, this is something for a much longer lecture that I'm teaching in different contexts. OK, so one thing that I really want to get across is why it's so complicated. Right? I'm telling you the model is complicated, but why is it complicated? Well, one of the reasons is that in order to have these invariant, that you never have two out-of-date copies, people employ rather complicated protocols. So one of them is called the Illinois protocol. And since we're in Illinois, I at least need to talk about it. Right? And by the way, since I went to ETH, I always have these Einstein quotes somewhere in my slides. So this protocol is rather simple. Right? However, well, let's see if I have enough time to explain it completely. So it's very, very simple. Keep this in mind. It's extremely simple. It just has a lot of states and a lot of state transitions. But every single of these state transitions is a very trivial thing. However, the combination of these state transitions applied to multiple different cache lines can get very mind-boggling at a time. Right? So, but what I want you to understand is the single transition of a single cache line, because then we're moving on to multiple transitions of multiple cache lines. Okay, so stay tuned. So what do we have? It's very simple. How many of you know the MISI cache coherence protocol?
We call it messy.
Well, you haven't. Yeah, okay. So you haven't seen the IBM cache coherence protocol. Because that is a crazy, okay. So I mean, if you want to have fun, there is a Power 7, Power 8 cache coherence protocol that you can actually look at the paper. It has not just 4 states, it has more than 12. And actually there are pair states, so it gets up to like 60 or something. So this is a simple version, right? and indeed, if you look at the Intel documentation, you will find something that's called MISIF, because they have an additional state. It's the forwarding state, which makes things slightly faster in certain circumstances. But I want you to understand that guy, because that's a simple one. And you can derive the other ones from understanding this protocol. Pretty simple, right? OK, so I have 2 goals with this lecture, by the way. 2 goals. One goal is you understand the powers of analytic mathematical abstract performance modeling. Because if you design an algorithm later, if you design a solver, you should be able to at least apply these methods. If you don't find an optimal solution, it's fine. But these methods, these log-P model and the model I'm explaining you now, you should at least be able to assess the performance of your protocol in this context, right? It's also very helpful if you write papers because it gets them accepted easier because it sounds like you're doing a real science, right? So it has multiple useful things for you. And the second thing I want you to understand, so this is the first part, right? The second thing is this, you should really understand how MISI works, right? We'll see. OK, but MISI is very simple. And so we have 4 states, right? And each of them has a nice name, right? So the first one is called modified. So the quick description of this state is, and this, oh, by the way, MISI, you run this protocol for every single freaking cache line in your system. Keep this in mind. If I have a cache and the cache has 10,000 cache lines, for each of these single cache lines, each of these cache lines will be in one of these 4 states. With the following updates, what I tell you, it will be applied to every single cache line in your cache, right? At the beginning, it was pretty mind-boggling for me. It's like, oh my God, I have like a bunch of these lines, and then they all are in these crazy states, and it gets pretty complicated. But let's focus on one for now, right? OK, so we have this guy. It can either be in modified state, which means that the local copy has been modified, and there are no copies in other caches, right? OK, it's pretty easy. And the memory is stale, so stale means outdated. OK. So the second state is exclusive, which is kind of clear. There's no copy in other caches, right? Because it's exclusive. But the memory is up to date. That's the difference. By the way, the naming is not totally intuitive, but it's OK. But the memory is up to date. At least you know that you don't need to flush it back if you invalidate it, right? Then the next one is shared. So you may have unmodified copies in other caches, right? And the memory is up to date. Right? So this is what you know about the state of your cache line. And the last one is the easiest. It's invalid, which means it's not in your cache, and you just don't know anything about it. You have to load it from memory. OK? Everybody following so far? Very good. OK, so then we have a little bit of terminology here. Where we have, and this is something you just know naturally. I mean, there's a clean line, which is a line that has not been touched. So you load it from memory, then it's a clean line. As soon as you update it, it gets dirty. Right? And then you suddenly know what a dirty line is. Okay? Then there's a bus transaction. This is something that you really do in the protocol in order to tell the other caches that you're doing something to this line. Right? For example, if I have a line that is in exclusive state and I write something to this line, what state do I have to put it in? Modified. Very good. And then I may need to tell other guys. Do I need to tell other guys in the exclusive state? Exactly, because it's your line. In what state do I need to tell other guys? Shared. Excellent. What do they need to do? Invalidate it. Very good. OK, so you already know the intuition what this protocol does. Right? And it is actually pretty intuitive. OK, so this is done through bus transactions. So actually, in the architecture I'm going to talk about, the Xeon Phi, there is a separate bus. There are actually two separate buses, and they're bidirectional. But OK, abstractly seen, there is one separate bus, right? And on this bus, which is different from the data bus, right? So this is the AKAD bus. OK, no details, fine. Let's just say it's the bus, right? And this bus transports all these update messages. Right? So there's a separate wire on the chip that transports these update messages. And then there's a separate set of wires. Of course, it's not just one wire. There's a set of wires on the chip that transports the data. Right? OK, keep that in mind. OK, good. And then you know locally read-write, it's just a store or load from a local CPU. It's pretty simple. OK, cool. But let me just quickly give you the intuition of how you now can construct this MISI protocol. And it's really nice. And and you have these states. Okay, and then you have state transitions. And usually I do it without the slides, but let me just do it quickly with the slides. Did you get the idea? And you can do it at home. You have the slides, I suppose. So if I see a local read, right, this is the first action that I can have. So now I look at all the states. What happens if I see a read in the states? If my line is in modified and I see a local read, of course I don't do anything because it's modified. I have it. It's fine. If it's in state exclusive, well, what should I do to the line? Because it's my line. If I read it, nobody cares. If it's in state shared, the same thing. However, if it's in state invalid, what do I need to do? Well, I need to read it from main memory, right? And I need to tell that I read it from main memory. Why do I need to tell that I read it from main memory? Oh, no, everybody's checking the slide, huh?
So others can share it.
Exactly. You need to send a bus signal that you're sharing it. So on a read, and what state does it go to? From invalid, it goes to? Why does it go to shared? It may go to shared, OK. Which other state may it go to? Exclusive, exactly. Depending on what? Depending on the other guy, how do I know? Well, I send a message through the bus to everybody else in the snooping protocol, right? And tell everybody, like, look, I'm reading this line, I'm reading this line. And then I wait a given time. It depends. On some architectures, you wait for a given time. Some architectures actually implement a handshake protocol, but it doesn't matter. I'm waiting for a reply, right? And if I don't get a reply, then I go to exclusive. If I get a reply, then I go to shared. OK? It's very intuitive. Next thing is essentially the same, right? Local writes. And this is the last one I'm doing because it takes too long for the others. So if I'm in modified, which means I already modified the cache line, so, well, I do nothing, right? Right? Oh, by the way, this is a read. And if I'm in E, well, pretty clear what I do, right? In E, because I'm now modifying it. Right? If I'm in S, so S means I own the line. It's my line, but somebody else owns it. So what do I need to do? Exactly. So now what you do is you send a bus read exclusive signal. Right? This is just called bus read for historical reasons. And what do you do then? What state do you move the line into? Oh, OK, exactly. OK, so now you can guess the remainder. And if it's invalid, of course, in invalid, you also go to modified, and you also send this bus read exclusive signal. OK, so now you understand. Now you can build a multi-core CPU. OK, at least the cache for a multi-core CPU. But everything else in the multi-core CPU is really the same as in the single-core CPU. I mean, this is the complex part of a multi-core CPU. OK, so you can now go and build this. And
you're not going to explain what to do if two cores are writing to their shared state at the same time, and when they try to request, they find out that another core is trying to write as well?
Well, that doesn't matter because it's atomic. Because they cannot write. I mean, in the abstract model, I know Intel internally does it slightly differently, but in the abstract model, you cannot actually perform the write before you have the line in M. So you acquire the line before, and then you do the write. So if somebody, and it may happen, and this is a very, very good point, thank you. It may happen that two write, what happens if two write at the same time? What do you think? So what do you think? No? You don't get crap. That's the beauty of this protocol. I'll handle you in a second. No. Let's say the cache line is in shared, okay? Two have it in their cache, and they're now writing at the same time. What happens? Exactly. One of them wins the race, and will go to M, and then the other one will win the race. Will not win, but will lose the race. But actually, the guy who lost the race will get its value into the cache line, right? And what will actually happen is the cache line will ping back and forth, right? If you have multiple writers, and we will see this, it'll ping back and forth, which is pretty stupid, by the way. Okay, well, it's an implication of the protocol. Okay, so, but what, yeah, okay, good. Yes.
It works.
Yeah, what makes one of them win the race? Is it because, like, we take turns riding on the bus line? Like, we just go around and around and around?
That's an implementation detail. It's a very good one. Well, certainly there are things, I mean, in the easy model, I would just say there's a bus lock, right? But that's really slow. Nobody does that in practice, okay? Even though there's an x86 instruction that's called lock, but it doesn't lock anything. It's again, historic. Let me talk about this offline, because I'm really running out of time. but I can exactly explain to you about offline. Okay, last.
So if you're in the invalid state when you attempt to do a write, wouldn't that not work because you don't actually have the data in your cache anymore?
Exactly. It's also a very good question. If you're in the invalid state and you do a write, what first happens is you do a bus read exclusive. So you first have to read it, and then you can write your data. There is something that Intel calls streaming stores that avoid the read. Right? So now you know, you've probably heard it that there is a streaming store assembly instruction. The only thing that does for you is you don't actually load the line and then write. What will this mean for the other data on the line if you do a streaming store?
It's stored in main memory as well, isn't it?
Yeah, but what is the other data? If I'm writing the first 4 bytes of a 64-byte line with my streaming store, what happens to the other 60 bytes? Junk. Exactly. So no, it's not really junk, but I mean, this is what your abstract model is, as you assume. Okay, so now you know a little bit about it. But I didn't want to go into that much detail, so we can talk about this offline, but I want to explain you how to actually use this model. So now you understand how this protocol works, right? Now you get this feeling. And now I tell you how to actually do something with it, because it's cool to understand the model, I understand. But how do you now develop an algorithm in this? You have no clue, right? I had no clue for over a year, so it's fine. And these other things you can handle at home if you want. And at the end, you will get this nice diagram, and you can also look it up on Wikipedia. So it's really general knowledge. And what you learned by now is that you cannot use this model. Right? It's because this is fundamentally different from this nice O and L model that I gave you before, which still applies to all MPI communication, essentially. Right? So keep that in mind. But in shared memory, it's slightly different. So how do I communicate something from a register in core 1 to a register in core 0 in core 2? How do I do that on, let's say, a Sandy bridge? So what you do, actually, is you pretend that you want to store this thing into an address in main memory. You pretend. You say store. But what the architecture will actually do is it'll store this thing into a cache line. Right? It'll go to modified state, right? And then it'll sit there. It'll not do anything if it's clever. Okay. And then the other guy, what it has to do, well, it has to read. And it's also, again, pretending that it's reading from main memory. But actually what's going to happen is the MECE protocol will transport that cache line over to this cache line, right? In the abstract model. And this is, by the way, the shortcut that the MECE model implies. If you use the MECE model, it'll do, it'll invalidate it here, it'll write it back here, and it'll read it back here. The MECE model with the forwarding state will directly forward the data. And this is what I'm going to talk about here, right? But this is a very simple modification of the ideal model, initial model. Okay, is that clear? So you're pretending you're writing to memory, but you're actually not. You're writing to your cache. And you're pretending you're reading from memory, but you're actually not, because you're reading from your cache. And the architecture will do the magic underneath. Right? And this is the thing that I want to make you understand, how to look at the performance of this magic. Right? This is the magic for correctness. And now let's look at the performance. How long do these things actually take? Right? So, and here I want to talk a little bit about the Xeon Phi thing, because this is a kind of a cool architecture, right? It has lots of cores on a single chip. You can buy it, and you have it at home. And it may be the next large-scale generation, because IBM is not doing that much. So we'll see. OK, so now let's look at this funny diagram. So this funny diagram is essentially how to transport a cache line from core 1 to core 2. So we have 2 cache lines involved, right? We have one memory address, and now it gets slightly complicated, mind-boggling. We have one memory address because both of them write to, let's say, 0, right? But we have 2 physical cache lines in 2 different states involved, because one is at core 1 and the other one is at core 2, right? Is that still clear? You should nod a little bit or something. OK, good. And then we can draw this diagram of pair states. So each of these 2 cache lines can be in different states. Now we know how this protocol works, right? So that's fine. And now we can actually look at these pair states. Well, if we want to transport a piece of data from cache line 1 to cache line 2, it could either be that cache line 1 is in state I and cache line 2 is in state I, or cache line 1 is in state E and cache line 2 is in state I. It can never be that both of them are in state E, right? Because that you know, because they can't both be exclusive in 2 different caches, right? And now we can just look at this and measure it for all the combinations, right? OK. So if we measure it for all on the Xeon Phi architecture, we get to this diagram. It's much simplified. And actually, we get 3 numbers. So the number to read an invalid line is 278 nanosecond on that architecture. Okay? And then that really depends a little bit on your memory, but for the one we measured, it's 278. A local read, if you have it in M, E, or S, costs you 8.6 nanoseconds. And now I know I break my promise. I'm giving you numbers, but it's OK. So bear with me. And the remote read, reading it from a remote cache, will actually take you 235 nanoseconds. Now you already see, well, that's not too much worse than actually an invalid read, right? And yes, that's true. So that's kind of a suboptimal feature. But I can explain it, but let's do this offline. So now we can actually come up with a model for a transport from 0 to 1. The model is very simple. We have a local read, a remote read, a remote read, and some overhead, right? And the estimation is 479 for this architecture, and the measurement is 497, so pretty close. So we can actually now model these transfers in the cache. We have numbers for them. Huh? That's a cool thing. And you see there are only reads, right? Nobody ever writes. In this protocol, there are actually no writes, right? You realize this. There are only bus reads, because a write means first a read, and then local update, and then another guy can only read it again. There's no real local remote write, right? OK, good. And then you can also do multi-line things, but let me skip this. And then you can instantiate the model. But this is rather simple. What you essentially do is you plug in this equation for the multi-line, and then you just do curve fitting to find the equation. I mean, every reasonable scientist knows how this works. It's regression. And then you can find these parameters. But again, I told you not to talk about parameters. The cool thing I want to tell you about, or the second cool thing about the Xeon Phi architecture, is actually that contention and congestion. So contention is for a resource that everybody really wants to access, and they know that they're contending for this resource. Congestion is if everybody wants to access different resources, but has to go through some kind of bottleneck, like the memory bandwidth, or what you just explained, which is like an indirect competition for resources, but it's not really up to you. So for example, here, a contention factor in the Xeon Phi, and this is the ring bus, by the way, right? So I kind of skipped this. Contention would be if everybody accesses the same cache line. That's contention. If everybody accesses different cache lines, but is limited by the bus bandwidth, then this is called congestion. Xeon Phi does not have congestion. Okay, good. Forget about it. Okay, now we're talking about contention. Contention we can essentially model this way. If we have C threads contending, and this B is really just the time it takes, is the latency, then we can again do the regression, and I don't have that much time, unfortunately. But you can see that contention can get pretty serious on this architecture, because you start out at 235 nanoseconds, like we had before. You go up to about 4 microseconds. Remember, on a reasonable cluster, you can get in 1 microsecond to the other side of the room, right? This is on chip. Okay, so contention is very serious. Okay, good. And now, as last thing, let me quickly explain you how to design a broadcast in that model. So we had the broadcast in the log-P model, right? So here in this model, it's slightly more complicated. So here we assume an algorithmic structure that is a tree again, right? So the tree is of height d. So there are d levels in the tree. And at each level of the tree, you have k. So this is the sum over d here, right? And at each level of the tree, you have kj. So j is the level index. Kj, what's it called, leaves in the tree, right? So here it's 3. Here it's 2, right? And so you can build your tree. And then the cool thing is now you can write down the equation in the model that we just developed in this RR, RL, and this C. Right? You can write down this equation, and that gives you the cost of the tree that has the parameters kj and d. Okay? What do you now do to find the optimal tree? Well, you have a cost function, and you have a shape. So what do? Very simple, one word. Optimization, yes. You optimize. Oh, so this is a minimization problem, right? So this is a constraint minimization problem because you want to reach at least that many threads. Oh, it's very simple. I mean, it just looks lots of equations, I know, but it's very simple. And then you solve for this problem, and then you design your algorithm based on this model. So if you now compare the broadcast algorithm that we just developed with Intel's MPI library here, and then we will see that this broadcast algorithm is much faster, right? So this is really competing with the optimized version of the Intel MPI library on their product, right? So we apply the model-guided optimization that we've seen, and we beat them by up to 50%, right? So we can do the same thing for other algorithms that I didn't talk about. So for barrier, for example, the MPI barrier for Intel MPI is really slow for some reason. OpenMP looks much better, but we still beat it in general. So you can see this is the black one line, and there's a box plots for experts, but I don't have enough time to go into this. So reduction is about the same. We get a significant speed up using this model-based design on this architecture, right? So this is more the motivation. I don't really care about the numbers, but you get faster than what the engineers are actually doing. So this is something that's kind of cool. So what did we learn while doing this, right? So we learned that model-based design is actually something that really pays off for two reasons. One reason is you really understand the architecture. But you understand it at a level that enables you to design algorithms on this architecture, right? So you can solve these optimization problems. You can solve them for log P. They're pretty hard optimization problems in some contexts. But now imagine you can express your algorithm, like your solver in such a model, and then you can solve for the optimal performance, right? So you apply the scientific method that you're applying on a day-to-day basis in order to extract the best performance out of your architecture. Right? And so this is really nice for log P. It gets pretty messy for cache coherence, as you've seen, because there are all these states. I mean, cache coherence is just much more complicated, much more bloated. I'm a big opponent of cache coherence, by the way, because it is so bloated. It's really hard to write a very good algorithm in a cache coherent system. It's really easy to write a bad one. It's very hard to write a good one. No, seriously, this is true. So actually, on Sandy Bridge, we've been doing the same thing. We get one more complexity. There's QPI as well. So it has different speeds. And there we get an improvement of up to 10x over the Intel MPI, or over Intel OpenMP and MPI. Right? So because this is so much more complicated. But the same principle gets us way further. But I would say cache coherence gets in our way. And then now the question is, there's actually a second part to that talk, which I may have no time to explain, of course. Do we need cache coherence? For scientific computing, my answer is no. For general purpose computing, my answer may be yes. But the idea is really that there's something that Bill and Rusty and Rajiv will be talking about tomorrow, just as a motivation, hopefully. You will learn about one-sided programming in MPI. This does not need cache coherence. This can be modeled with the log P model that I explained at the very beginning that I only wasted 5 minutes on because it's so simple. Right? So it's a huge simplification that you can make just applying the right programming principle. And the cool thing about this is that you will be safe if you use this one-sided programming, or whatever UPC. I am an MPI guy, I admit it, but I also accept other programming models. So you can do that. And you're safe for future architecture. So if anybody ever decides to suddenly get rid of cache coherence, then you're just like, oh, sure, no problem, because I can already do it. Right? OK, with that, I want to be open for questions. And there's already a question.
If you don't have enough memory, if you use MPI only, you need a lot of memory.
This is a very good question. So what I'm just saying is not to duplicate data structures. I'm just saying that you should not rely on cache coherence. And that means you can still access remote data directly, right? But you should just not rely on something to transport the data implicitly for you just because you're reading and writing it at 2 different locations. Right? This whole MISI protocol is really overkill for scientific computations. It's really, really helpful, and don't get me wrong, it's really helpful if you write a database or something like this, because there the data structures get very involved. But for high-performance computing, we know how to do domain decomposition.
But
yes?
When you have many cores,
yes.
You will not have enough memory if you don't have this coherence protocol.
Why do you not have, why can't you just decompose your domain among these cores? You will not duplicate anything. Remember, you can still access the other guys. It's just not coherent, which means you have to manage the access yourself. It makes the programming slightly more complicated. It has no memory overhead whatsoever. Right? But Bill and Rajiv and Rusty will tell you everything about it, so that's not my role. Okay, so do we have any questions, comments, concerns?